A man is trapped on a frictionless surface. Zero friction. How does he get off? That's the question I want you to ponder as we take a look at Newton's third law of motion. Here it is. Newton's third law, chapter 7, states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first one. I'm going to give you an example where this is true, and I'm also going to give you a non-example, one where that's not what's being talked about. I'll show you first an example. If you push against the wall holds you up, doesn't it? So you push on the wall pushes on you. This is a very simple demonstration of Newton's third law. Let's not be confused with something that we've talked about in chapter 2. In chapter 2, we talked about static equilibrium and all forces canceling out. In this picture, we do have two forces that are equal and opposite, but they are not example of Newton's third law. You got to be able to figure out why that is. I'll help you. In this case, we say that the red vector represents Earth pulling on Bob, and the green vector is the floor pushes Bob. We called that green vector a support force. Why isn't this Newton's third law? It's because when we are trying to identify action and reaction pairs, we can't switch the tune. What do I mean? Well, on the left side, we've got Earth pulls Bob. So over on the right side, all we really should have there is that Bob pulls Earth. Alright? That would be an example of Newton's third law. This is not. Be very careful. This is a confusing chapter. You may have to spend some time reading about the different examples they go through in the text. In Newton's third law, we describe a relationship between two forces. Okay? One of the forces we typically call the action force, and one is called the reaction force. Neither force exists without the other. They are equal in strength and opposite in direction, and they occur at the same time. Newton's third law often is stated for every action there is always an equal and opposite reaction. But it doesn't really matter what you call the action or the reaction. Alright? So you don't have to worry too much about that. Alright. To identify the pairs of an action-reaction force, first you must identify the interacting objects, such as A and B, whatever they are. And if the action is A acting on B, then you just have to flip that around and say B acts on A. That's how that one non-example, that didn't do that, did it? It said Earth attracts Bob. That was true. And it says floor pushes Bob. Also true. But that's not what we're talking about here, because all of a sudden we switched. We were talking about Earth and Bob, and then all of a sudden we're bringing the floor. Okay? So that's a different object, some other object C. Only dealing with two objects and their interactions with each other. So if we're going to be strict about this, it's always going to be very easy, actually. It's going to be a very simple recipe to follow. the action will be stated something like object A exerts a force on object B. And the reaction will be object B exerts a force on object A. Okay? Let's put it into practice here once. Here we've got, let's try looking at this one here. We've got a force vector here. The tire pushes the road. Well, what would be the reaction? The tire pushes the road. It's not hard, folks. Just flip it around. The road pushes the tire. The tire is connected to the car goes, right? So that's not too bad. Here's another one. See if it works for this one. The action is that the rocket pushes gas. Gas is some propellant shooting out the back. Does the gas push on the rocket? Yes, that's the reaction. In the third example, the action is Earth pulls the ball. The ball accelerates down towards Earth. What's the reaction? Did you say ball pulls Earth? That might seem strange. The ball pulling on the Earth? What? We'll talk more about some of those types of things later, where there's a huge mismatch in mass and what the result is of those types of situations, just to try to clarify. But yeah, that's it. The ball pulls on the Earth. That's the reaction there, folks. Let's think about this one. You've got the Earth, huge, right? And you got the moon. Still huge, but relative to the Earth, it's quite small. The gravity on the moon is less than the gravity that we experience on Earth. So let's think about this in terms of a third law problem. And this, I think, illustrates how they can kind of be confusing. Okay, we know that Earth pulls on the moon. But does the moon also pull on the Earth? And if so, which pull is stronger? Don't be tricked by this kind of language, okay? Of course the moon pulls on the Earth. Newton's third law says that it has to. The Earth pulls on the moon, and the moon pulls on the Earth. Equal and opposite forces. Equal and opposite forces. So which pull is stronger? Neither. Don't be tricked. Just because Earth's bigger doesn't mean that it's going to pull harder. That would be impossible. Okay? The moon pulls just the same on Earth as Earth pulls on it. I know, it sounds strange, but it's not very difficult if you just follow the rules. Okay? You'll get to try this one in your quiz that comes after this video. What do you think? Is it similar to the one we just saw with the moon and the Earth? Okay? Think about that one. When a ball is being pulled down to the Earth, I said that the Earth is being pulled by the ball. But we don't feel the Earth moving towards the ball. And in class I'll go through an example and describe why that would be almost impossible. But here's an example where the two objects are a little bit closer in size. We've got a cannon and a cannonball. Now, a cannonball is heavy. I mean, if you tried to pick it up, it'd be kind of like little shot puts I've got in my room. But the cannon is quite a bit more massive. So the way this plays out is you kind of have to take a look at how it plays out using Newton's second law. Alright? So we've got a force on the cannon equal and opposite to the force on the cannonball. Here we've written those with the same size font, okay? But what's different is that the cannonball, relative to the cannon, has a small mass. The cannon has a rather large mass. So what ends up playing out here is that they both go opposite directions because there's forces acting on them, but the cannon's mass being so big, when you divide F by a large M, you get a small a, folks. And over here, that same force now, divided by a small m, gets a large acceleration. So that's kind of how this works, is what you observe is accelerations, right? You see things moving. And that part doesn't have to be equal. Newton never said that it did. But the forces do. Okay, a balloon, you've certainly tried this before. A balloon goes flying all over the place. When it squeezes on those air particles inside of it, it launches a bunch of gas particles out the back. But those gas particles could be viewed as tiny little cannonballs. Really. In one sense, you could think of it like that. And so here we have another situation where the gas is getting pushed out, and I should say it this way: the balloon pushes on the gas, and the gas pushes on the balloon. All right. So that's basically how Newton's third law kind of works. I've got a few more videos for you to watch, but let's go back to our original question before we leave. Here's our guy. How does he get off? Well, he's only got one thing on him that's going to help him, folks, and that's his shorts. If he takes off his shorts and he throws them, he'll put a force on his shorts. But here's the good news. The shorts will also put a force on him. And so he will, during that time when they're in contact, accelerate backwards, and objects in motion tend to stay in motion, so he'll stay in motion and he'll eventually get to the edge and be able to pull himself off. There'd be no other way. Well, maybe one other way. If you can think of it, you tell me in class. Alright, that's it for now.